Now let's take a look at the root functions, which we've seen before. We've talked about them in our family of functions. If I have an even root function, my domain is 0 to infinity. If I have an odd root function, my domain is all real numbers. And the higher the root, the bigger that index is, the more slowly the graph increases when x is greater than 1. So this could be seen mostly comparing x to the 5th here with x squared. X squared grows more. When we reach 4, we're at 2. But for the 5th root of x, when we reach 4, we're barely above 1 on the output. So that's what that last statement means in part C. Let's evaluate the root function for given values. Evaluate means we're going to take the number and plug it in. You've done this before. Pause the video, try it on your own. See if you get the same answers that I get. Did you pause it? Did you get some answers? Let's work through it. F of 28, cube root of x, but x is now 28, minus 1. 28 minus 1 is 27. Cube root of 27 is 3. F of 9, cube root of 9 minus 1. Cube root of 8. Cube root of 8 is 2. F of 0, cube root of x minus 1, 0 minus 1. Cube root of negative 1 is negative 1. Did you get number 10? Good. 11, same idea. G of 11, negative square root 2 times 11 plus 3, negative square root 22 plus 3. 22 plus 3 is 25. Square root of 25 is 5, but I have a negative on the outside. G of negative 1. I'm going to move these over here just so that I make sure I have enough room. G of negative 1, negative square root 2, negative 1 plus 3. Negative 2 plus 3. Negative 2 plus 3 is 1. Square root of 1 is 1. I've got the negative on the outside. Giving myself a little bit more space for the last problem. G of negative 2, negative square root 2 times negative 2 plus 3. 2 times negative 2 is negative 4. Negative 4 plus 3 is negative 1. Here I'm trying to take the square root of a negative number. This is not real. Now let's look at a couple of word problems that go along with these power functions, these root functions that we've been working with. Here we're modeling the surface area of the human body. The surface area of a person who is 66 inches tall and weighs W pounds can be estimated by this formula. S of W equals 327 W to the power 0.425, where S is in square inches. Find S if this person weighs 130 pounds. So we would plug in 130 for the weight. 327 W to the power 0.425. I could try to estimate it here. 130 on the graph, following it across between 2,000 and 3,000. But here's where a calculator will definitely come in handy. So pull those calculators out. Plug in 130.425. I'm going to do my best to try to help on the Windows Scientific Calculator. The operations should be similar to your calculators, but you may have functions that look a little bit different from mine. So I'll try to point you to the right one when we get there. Looking at this to simplify it, first, in the order of operations, the first thing I need to do here is that exponent. So we'll pull up our calculators, 130, and I want to raise it to the 0.425 exponent. So you're either going to look for an x to the y function, x to the power y, or you look for a button that looks a lot like the shift symbol on your 6 key on your keyboard. That guy. Your calculator may have that. That's called a caret. Your calculator may have the y and the x reversed, but it looks like this, y to the power x. That's another indication that we're raising it to another power. So 130, oh, you can see the caret in that calculator way up top here. 130 to the power 0.425. And I hit enter. and we get something crazy long. I'm not going to write that down because I need that number. I'm going to multiply that number times 327. So this 7.9 is 130 to the power of 0.425. So I multiply. I did not type it in. I just hit multiply. Multiply, that's my next operation. 327. Enter. That's the answer I want. 2,588. Maybe 0.1, maybe not. There's no guidance on how to round it. We'll keep it as a whole number. If the person gains 20 pounds, by how much does the person's surface area increase? Well, let's start out by having that person gain 20 pounds. And we need it on our calculator again. 150 to the power 0.425. And we get 8.41 and stuff. But we need to multiply that by 327. 2,750.3. So we wouldn't round up. And the last question for this problem, a graph is shown of this function. Suppose a person's weight is more than 50 pounds and it doubles. Use the graph to determine if the person's surface area also doubles. If I'm at 50 pounds and I look at 100, what a double is, that difference surely is not indicating twice as much. I could compare 200 to 400. Looking at 200 to 400, indeed this gap right here between them is not twice what I started when I plugged in 200. The person's surface area does not double. Here's another example we can consider, modeling wingspan. Biologists have found the weight of a bird and the length of its wingspan are related. So L of W equals K times W to the 1/3, where K is a constant. K could be the bird's constant, for example. We look at the type of bird that it is, and it has its own number. Part A says use the data to approximate the value of K. In our function notation, we need to find that K. How do we do it? We try plugging in these numbers. If we plug in 0.1, and set it equal to 0.422, we can find a value for K. Try this on your own and see if you can answer these 3 questions about wingspan for a bird.